Alright, um, this video we are going to do, I'm not sure if this is technical or not technical, but I found the top of Hiker News, and well, now it's not the top anymore, and the title caught my attention, and it's relatively short. There's not much math in it. Also, we need to do a reinforcement learning video as well because we're a little bit behind on that. So let's just do the routine. Let's go to about. Let's get rid of that. Make this bigger. Just a little bit like that. And I don't know why. Let me just double check something. Yes, I can. Yeah. Well, some people went deaf. Well, that's fine. Oh yeah, I don't know why the YouTube video quality dropped so much. This is a 2K monitor, whatever that means, if I remember, and the resolution is pretty good. I can't lie, but when you upload, I can't watch myself on YouTube, on TV. It's terrible. Anyways, okay, so he's a scientist. Whoa. Alright. I'm a scientist with a background in physics, neuroscience, education, planetary science, and especially machine learning. My biggest claim to fame is that I invented diffusion-based generative models. My most interesting job requirement is that I once had to wake and sleep based on Martian sunrise and sunset for 3 months. Now that I've established that I have credentials in machine learning. Who's this guy? Joshua Soltikstein. Slightly more professionals. Interesting. Art projects. Okay. Research projects. I see. And about him, pretty cracked. What it says Joshua is most infamous for inventing diffusion mode. How come I've never heard about this guy? Please don't take it if I don't get back. Please make an informed decision how much time to spend writing to me. Okay. Joshua is most famous for inventing diffusion models. I feel very ignorant. Deep, unsupervised learning using non-equilibrium thermodynamics. Alright, everything starts with thermodynamics. His recent work has focused on theory of over-parameterized neural networks, meta-training of learned optimizers, and understanding the capabilities of large language models. Joshua recently joined Anthropic as a member of technical staff. He has previously worked as principal scientist in Google Brain and Google DeepMind, as a visiting scholar in Surya Ganguly's lab at Stanford University, and as an academic resident at the Khan Academy Education Nonprofit. He earned his PhD in 2012. Joshua. That's a German name. I'm probably butchering it. The Redwood Center for Theoretical Neuroscience at UC Berkeley in Brno Olszewski's lab. Prior to his PhD, he worked on sending rovers to Mars. That's fair. Alright, so he has some authoritative, what's it called? I need to get that post there, the one that says like fallacies. So he must know what he talks about. Alright. 2022. Okay. Increased efficiency can sometimes counterintuitive. Too much efficiency makes everything worse. Overfitting and this strong version of Goodhart's law. So basically, overfitting is like when your model becomes very specific to what the data was. That if your new data is a little bit different, it messes it up, categorize it wrongly, and all of that. Increased efficiency can sometimes counterintuitively lead to worse outcomes. This is true almost everywhere. We will name this phenomenon the strong version of Goodhart's law. As one example, more efficient centralized tracking of student progress by standardized testing seems like such a good idea that well-intentioned laws mandated. What is Goodhart's law? Alright. Goodhart's law is an adage often stated as when a measure becomes a target, it ceases to be a good measure. It is named after British economist Charles Goodhart, who is credited with expressing the core idea of the adage in a 1975 article on monetary policy in the United Kingdom. Any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. It was used to criticize the British Thatcher government for trying to conduct writing ideas down. If I'm gonna do maybe some stickman things, videos on some critical people. Okay, put Thatcher there. Alright, numerous concepts are related to this idea, at least one of which. So it says any observed statistical regularity will tend to collapse once pressure is placed upon it for control purposes. So when there's a pattern and you want to control the pattern changes. Is that what he's trying to say? I don't know. Why is this not working? I'm going blind. Great. Anyways. However, testing also incentivizes schools to focus more on teaching students to test well and less on teaching broadly useful skills. As a result, it can cause overall education outcomes to become worse. Similar examples abound in politics, economics, health, science, and many other fields. This some counterintuitive relationship between efficiency and outcome occurs in machine learning, where it is called overfitting. Overfitting is heavily studied, somewhat theoretically understood, and has well-known migrations. This connection between the strong version of Goodhart's law in general and overfitting in machine learning provides a new lens for understanding bad outcomes and new ideas for fixing them. Alright, machine learning overfitting is a pervasive phenomenon. We want to train an ML model to achieve some goal. We can't directly feed the model to the goal, so we instead train the model using some proxy which is similar to the goal. Okay. This is the thing I care deeply about. We must optimize it. That thing is immeasurable and possibly ineffable. What is that? Ineffable. Ineffable too great or extreme to be expressed or described in words in a fable. But look, this thing near it is easy to measure. What if we optimize that instead? Great idea. For instance, as an occasional computer vision researcher, my goal is sometimes to prove that my new image classification model works well. I accomplish this by measuring its accuracy after asking it to label images. Is this image a cat or a dog or a frog or a truck or a? From a standardized test dataset of images, I'm not allowed to train in my model on the test dataset though. That would be cheating. So instead, train the model on a proxy dataset called the training dataset. I also can directly target prediction accuracy during. So I instead target proxy objective, which is only related to accuracy. For those wondering, this is apple juice. I'm just too lazy to wash glasses. I'm not gonna read these tipsy. I promise you that. So instead trained on that, so I instead target a proxy objective which is only related to accuracy. So rather than training any model on the goal I care about, classification accuracy on the test data set. Instead training and using that training and test data set, and it wasn't another data set. How do we split our validation set? Oh yeah. Use the training set to feed the model, the validation set to tune the model hyperparameters, and test to valid. Alright. As we continue, okay. Peace, love, and puppies, objective we care about. Proxy objective we know how to measure and optimize. Yay, the thing I care about is improving. So the loss is going down as time goes there. As we continue optimizing the proxy though, we eventually exhaust the usable similarity between proxy and the goal. The proxy keeps on getting better, but the goal stops improving. In machine learning, we call this overfitting. But it's also an example of Goodhart's law. Goodhart's law states that when a measure becomes a target, it ceases to be a good measure. Give an example, and Goodhart proposed this in the context of monetary policy, but it applies far more broadly in the context of overfitting in machine learning. It describes how the proxy objective we optimize ceases to be a good measure of the objective we care about. The strong version of Goodhart's law: as we become too efficient, the thing we care about grows worse. If we keep on optimizing the proxy objective even after our goal stops improving, something more worrying happens. The goal often starts getting worse, even as our proxy objective. What am I reading? If we keep on optimizing, the strong version of Goodhart's law: as we become too efficient, the thing we care about grows worse. The goal often starts. I feel like these sentences are out of it, story. Give us the story too, man. Give us something. Not just a little bit worse either. Often the goal will diverge towards infinity. Okay, this is an extremely general phenomenon in machine learning. It mostly doesn't matter what our goal and a proxy are or what model architecture we use. If we are very efficient at optimizing a proxy, then we make the thing it is a proxy for grow worse. Through this phenomenon is often discussed, it doesn't seem to be named. Let's call it the strong version of Goodhart's law. We can state it as when a measure becomes a target, if it is effectively optimized, then the thing it is designed to measure will grow worse. Goodhart's law says that if you optimize a procuracy, eventually the goal you care about will stop improving. Eventually going strong version of Goodhart's law differs in that it says that as you over optimize, the goal you care about won't just stop improving, but will instead grow much worse than if you had done nothing at all. Oh, it gets worse. Goodhart's law applies well beyond economics, where it was originally. Alright, Goodhart this, Goodhart that. Ooh, I like that. Maybe. I don't know. Goodhart. Goodhart. I believe it can help us understand failures in economies, governments, and social systems. Increasing efficiency and overfilling are happening everywhere. Increasing efficiency is permeating almost every aspect of our society. If the thing that is being made more efficient is beneficial, then the increased efficiency makes the world a better place. Overall, the world seems to be becoming a better place. If the thing that is being made more efficient is beneficial, then the increased efficiency makes the world a better place. Overall, the world seems to be becoming a better place. If the thing that is being made more efficient is socially harmful, then the consequences of greater efficiency are scary or depressing. Think of mass surveillance or robotic weapons. What about the most common case though, where the thing we are making more efficient is related but not identical to beneficial outcomes? Alright, is related but not identical to beneficial. Okay, what happens when we get better at something which is immediately correlated with outcomes? With outcomes we care about. In that case, we can overfeed. The same as we do in machine learning, the outcomes we care about will improve for a while, then they will grow dramatically worse. Below are a few possible facile. I hope that's Italian. Facile. Examples applying this analogy. Educate children well. Go. Measure students and educate school performance on standardized tests. Strong version of Goodhart's law leads to schools narrowly focus on teaching students to answer questions like those on the test at the expense of the underlying skills the test is needed to measure. Rapid progress in science. Pay researcher a cash bonus for every publication of incorrect or incremental results, collusion between reviewers and authors, research paper mills, a well-lived life, maximize the reward path in the brain, substance addiction, gambling addiction, days lost to doom scrolling into Twitter. Healthy population, access to nutrient-rich food, obesity epidemic. Goal: leaders that act in the best interests of the population, leaders that have the most support in the population, leaders whose expertise and passions centered narrowly around manipulating public opinion at the expense of social outcomes. Um, these are interesting. I have some opinions, but I hope it doesn't end there. Okay. Goal: an informed, thoughtful, and involved populace, the ease with which people can share and find ideas. Strong version of Goodhart's law leads to filter bubbles, conspiracy theory, and parasitic memes, escalated tribalism. Goal: distribution of labor and resources based upon the needs of society. Capitalism. Strong version of Goodhart's law leads to. What was the. Okay, I need to memorize this. When we measure. Yeah. Okay, so what was. Where's the strong version, dude? Give me the strong version. Where was it? When measuring target, we efficiently. Oh, when a measure becomes a target, if it's efficiently optimized, then the thing it is designed to measure, the thing it's designed to measure will grow worse, or the way that it measured that thing grows worse. Yeah. Anyways. Okay. As an exercise for the reader, you can think about the strong version of Goodhart's law would apply to other efficiencies like the ones in this list. Telepresence and virtual reality, personalized medicine, controlling everyone. Controlling everyone. Tailoring marketing messages to the individual customers or voters who will find the most actionable. Predicting the outcome of elections. Actionable writing code, artificial intelligence, reducing slack in supply chains, rapidly disseminating ideas, generating entertainment, identifying new products we'll buy, raising livestock, trading securities, extracting fish from the ocean, constructing cars. Okay. Make slower money, crash the market. Extracting fish, kills all fish. Constructing car. It's a little bit hard article. Yeah. How do we mitigate the problems caused by overfitting and the strong version of Goodhart's law? If overfitting is useful as an analogy, it will be because some of the approaches that improve it in machine learning also transfer to other domains. Below, I review some of the most effective techniques from machine learning and share some thoughts about how they might transfer. Mitigation. Better align proxy goals with desired outcomes. In machine learning, this often means carefully collecting training examples which are as similar as possible to the situation at test time. Outside of machine learning, this means changing the proxy we have control over. Example, laws, incentive, and social norms. So that they directly encourage behavior that better aligns with our goals. This is the standard approach you use to try to engineer social system. Mitigation. Add regularization penalties to the system. In machine learning, this is often performed by penalizing the squared magnitude of parameters. so that they stay small. Importantly, regularization doesn't need to directly target undesirable behavior. Almost anything that penalizes deviations of a model from typicality works well. Outside of machine learning, anything that penalizes complexity or adds friction or extra cost to a system can be viewed as regularization. Some example ideas: add a billing mechanism to SMTP so there is a small cost for every meal. Use a progressive tax code so that unusual success is linked to disproportionality created costs. Charge a court fee proportional to the squared number of lawsuits initiated by an organization so that the unusual use of the court system leads to unusual expenses. Tax the number of bits of information stored about users. So it just says keep things small. This sounds European. Well, what can I do? Why is this like that? Why is the LaTeX not LaTeXing? Alright, inject noise into the system. In machine learning, this involves adding a random jitter to the input, an internal state of a model. The unpredictability resulting from this noise makes overfitting far more difficult. Here are some ideas of how to improve outcomes by injecting noise outside of machine learning. Stack rank all the candidates for a highly competitive school or job. Typical offers would be made to the top K candidates. Instead, make offers probabilistically with probability proportional to approximately number of top tier candidates divided by candidates stack rank. Benefits include greater diversity of accepted candidates, less ridiculous resources spent by the candidates tuning their application and by application reviewers reviewing the application. Since the small changes in assessed rank will have a small effect on outcome probabilities, occasionally you will draw a long shot candidate that is more likely to fail, but also more likely to succeed in an unconventional and unusually valuable way. Randomly time quizzes and tests in a class rather than giving them on a pre-announced dates so that the students study to understand the material more and cram for the test less. Require securities exchange. To add random jitter to the times when they process trades with a standard deviation of about a second. An efficient market is great. Building a global financial system out of a chaotic, non-stationary, dynamical system with a characteristic timescale more than 6 orders of magnitude faster than human reaction time is just asking for trouble. Randomized details of the electoral system on voting day. In order to prevent candidates from overfitting to incidental details of the current electoral system by taking unreasonable positions that appeal to a pivotal minority. by taking a reasonable position that appeal to a pivotal minority. For instance, randomly select between ranked choice or first past the post ballots, or randomly rescale the importance of votes from different districts. I'm not saying all of those are good ideas, just ideas. We are reading your ideas. Mitigation, early stopping. Machine learning, it's common to monitor a third metric besides training loss and test performance, which we call validation loss. When the validation loss starts to get worse, we stop training. Even if the training loss is still improving, this is the single most effective tool we have to prevent catastrophic overfitting. Here are some ways early stopping could be applied outside of machine learning. Sharply limit the time between a call for proposals and submission date, so that proposals better reflect pre-existing readiness. And to avoid that effect, we're increasing resources are poured into proposal generation rather than being used to create something useful. Whenever stock volatility rises above a threshold, suspend all market activity. And to avoid an effect where increasing resources are poured into proposal generation. Alright. The use of antitrust law to split companies that are preventing competition in the market. Estimate the importance of a decision in dollars. And the value of the time you have already spent analyzing the decision approaches that value. Make a snap decision estimate. Freeze the information that agents are allowed to use to achieve their goals. Press blockouts in the 48 hours before an election might fall under this category. Alright, one of the best understood causes of extreme overfitting is that the expressivity of the model being trained too closely matches the complexity of the proxy. I would like to read these. Read the comments. Yes, you should read the comment. Alright. When the model is very weak, you can only make a little bit of progress on the task, and it doesn't exhaust the similarity between the goal and the proxy. When the model is extremely strong and expressive, it can optimize the proxy objective in isolation without inducing extreme behavior on other objectives. When the model's expressivity roughly matches the task complexity, the number of parameters is no more than a few orders of magnitude higher or lower than the number of training examples. Then it can only do well on the proxy task by doing extreme things everywhere else. See figure 1 for a demonstration of this idea on a simple task. This cause of overfitting motivates two final diametrically opposed methods for mitigating the strong version of Goodhart's law. Alright. Losing focus. Alright, let's just read the last sentence. When the model's expressivity roughly matches the task complexity, The number of parameters is no more than a few orders of magnitude higher or lower than the number of training examples. Then it can only do well on the proxy task by doing extreme things everywhere else. See figure 1 for a demonstration of this idea on a simple task. This cause of overfitting motivates two final dramatically opposed models of methods for mitigating the strong version of Goodhart's law. Mitigation: restrict capabilities / capacity. In machine learning, this is often achieved by making the model so small that it's incapable of overfitting. In the broader world, we could similarly limit the capacity of organizations or agents. Examples include campaign finance limits, set a maximum number of people that can work in companies at a given time, allow only 10 people to work in any lobbying group, set the maximum number of parameters or training compute that any AI system can use. The way he talks about government and AI is almost like AI is going to be our government. That's just a random thought. Anyways, mitigating, increase capabilities and capacity. Mitigation. In machine learning, if a model is made very big, it often has enough capacity to overfit to the training data without making performance on the data worse. In the broader world, this would correspond to developing capabilities that are so great that there is no longer any trade-off required between performance on the goal and the proxy. Examples include obliterate all privacy and make all the information about all people, governments, and other organizations available to everyone all the time, so that everyone can have perfect trust of everyone else. This could be achieved by legislating that every data set database be publicly accessible and by putting cameras in every building. To be clear, from my value system, this would be a dystopian scenario. Invest in basic research in clean energy, develop as many complex, indestructible, and diverse market trading instruments as possible, investing on as many timescales as possible. In nature, more complex ecosystems are more stable. Maybe there is a parallel for markets. Use the largest, most compute and data intensive AI model possible in every scenario. The last mitigation of just continue to increase capabilities works surprisingly well in machine learning. It is also a path of least resistance. Trying to fix our institutions by blindly making them better at pursuing misaligned goals is a terrible idea, though. Alright. Parting thoughts. The strong version of Goodhart's law underlying most of my personal fears around AI, expect a future blog post about my AI fears. If there is one thing AI will enable, it is greater efficiency on almost all tasks over a very short time period. We are going to need simultaneously deal with massive numbers of diverse unwanted side effects, just as our ability to collaborate on solutions is also disrupted. There is a lot of opportunity to research solutions to this problem. If you're a scientist looking for a research idea which are pro-social and have the potential to create a whole new field, you should consider building formal mathematical bridges between results on overfitting in machine learning and problems in economics, political science, management science, operations research, and elsewhere. Okay, this is a gold mine waiting to be tapped. I might actually be suggesting here that we should invent the field of psychohistory. and that overfitting phenomena will have a big role in that field. Does this go to psychohistory? It's I have his book, Asimov. Well, it might not be from Asimov, but psychohistory. Oh, come on, Asimov should be here, right? Oh, it's there. Anyways, okay. The more social systems break due to the strong version of Goodhart's law, the less we will be able to take the unconcerted rational action required to fix them. Hopefully, naming and better understanding the phenomenon will help push in the opposite direction. Models often suffer from the strong version of Goodhart's law and overfit catastrophically when their complexity is well matched to the complexity of the proxy task. If a model is instead much more or much less capable than required, it will overfit less. Here, models are trained to map from a one-dimensional input X to a one-dimensional output Y. All models are trained on the same 10 data points in red. The model with 4 parameters is too weak to exactly fit but it smoothly approximates them. The model with 10,000 parameters is strong enough to easily fit all the data points and also smoothly interpolate between them. The model with 10 parameters is exactly strong enough to fit the data points, but it can only contort itself to do so by behaving in extreme ways away from the training data. If asked to predict y for a new value of x, the 10 parameter would perform extremely poor. For details of this toy experiment, which uses linear random feature models, you see this collab. Really? Alright. Is it right or is it wrong? I don't know. I don't trust that. There is a gut feeling that I don't trust that. Anyways, accuracy is not differentiable, which makes it impossible to target by naive gradient descent thinking training. It is usually replaced during training by a proxy of softmax cross entropy loss, which is differentiable. There are black box training methods which can directly target accuracy, but they are inefficient and rarely used. This modern phrasing is due to Marilyn Strathern. It's coming from later. Alright. It's a little bit of random article, but let's see the comments. Alright. Interesting timing for me. Just a couple of days ago, I discovered the work of biologist Olivier Hammond, who has been raising exactly this issue. His main thesis is that very high performance, which he defines as efficacy towards a known goal plus efficiency, and very high robustness, the ability to withstand large fluctuations in the system, are physically incompatible. Examples abound in nature. Contrary to common perception, evolution does not optimize for high performance but high robustness. Giving priority to performance may have had sense in a world of abundant resources, but we are now facing a different period where instability is the norm. We must and will be forced to backtrack on performance in order to become robust. It is the freshest and most interesting take on the poly crisis that we have seen in a long time. Alright. Too many comments. Is there any way to close? Okay, that one has. I don't know how they sort these. Let's go with this. 6 hours, it was the longest too. Okay. You can add a measure of robustness to your optimization criteria. You can explicitly optimize for having enough slack in your utilization to handle these unforeseen circumstances. For example, you can assign priorities to the loads on your systems so that you can shed lower priority loads to create some slack for emergencies without having to run your system idle during lulls. I get what the article is trying to say, but they shouldn't write off optimization as easily as that. The problem is that people who agree to a task being low priority still expect it to be done in 9 months, and all of a sudden they become high priority if it doesn't happen. So you're fixing the microeconomics of the queue but not the macro. Queues still suck when they fill up, even if they fill up last minute jobs. What is he talking about? What are we talking about? Is that like responding or 6 hours ago? Oh, what? Yeah. Why did they open that? Oh, it's there anymore. Okay, so there is a bunch of Alright, I find this article a bit odd considering what the author is an expert in generative imagery. It's the exact problem it discusses, the lack of a target that is measurable. Defining art is well known to be ineffable, yet it often agreed upon. For thousands of years, we've been trying to define what good art means, but you do not get good art by early stopping. You do not get it by injecting noise. You do not get it by regularization. All these do help and are essential to our modern processes, but we are still quite far. We have better proxies than FID, but they all have major problems and none even come close, even when combined. We've gotten very good at AI art, but we are still got a long way to go. Everyone can take a photo, but not everyone is a photographer, and it takes creative skill and expertise to take such masterpieces. Yet there are masters of the craft. Sure, AI might be better than you at art, but that doesn't mean it's close to a master. As unintuitive as this sounds, this is because the skill isn't linear. The details start to dominate as you become an expert. A few things might be necessary to be good, but a million things need to be considered in master, because master is the art of subtlety. But this article, it sounds like everything is nailed. We don't have the methods yet, and my fear is that we don't want to look. There are of course many pursuing this course, but it is very unpopular and not well received. Scale is all you need is quite exciting, but lacking sufficient complexity, which even Sutton admits to be necessary. Well, Sutton is the guy we are reading his book, by the way. It's my fear that we get too caught up in excitement that we become blind to our limitations, because it's knowing those limitations that is what gives us direction to improve upon. When every critique is seen as spoiling the fun of the party, we'll never be able to have anything better. I'm not trying to stop the party. In fact, I'm worried it will stop. In the process, okay, it's getting exciting. In the process, acting somewhat like a generalization of the problem it describes. Overly precise and narrow approaches to improve ineffable qualities, but the author seems to understand that. He comments on the absurdity of some direct transfer of ML methods to real-world problems. I think he just added a bunch of not necessarily well solvable, but particularly suffering from overfitting example problems. It's a food for thought article, not a grand proposal. Okay. Really interesting article, got me pondering the extent to which the peacock's tail in an example of overfitting in Good Hearts. The female peacock is using the make peacock's tail as a proxy for fitness, which beautiful consequences, but the males with the largest, showiest tails are clearly less fit. Galdrat. Who's that guy? Was an Israeli business magnate guru who was the originator of the optimized production technique, and then the theory of constraints, the thinking process, drum buffer rope, critical chain project management. Alright, so let's just go over the points. Learn about Goldhart. Learn about overfitting. Don't do that. He talked about the transferring of knowledge from machine learning and mathematical bridge to soft sciences and management operations. Yeah, man, operations used to mean something like fixing someone's rib or like stomach or heart. But now it's just, we have operations. Welcome. What else? What else? Accusing these examples of involving bad proximity is identical to the no true Scotsman fallacy. Yeah, and we learned that he's the guy behind diffusion generative models. He did that with thermodynamics. And what else? Jashaw. So Dickstein. He's also in GitHub there, just like me. Winning the war, losing the battle. Alright, yeah, I don't have much opinion on this. I'm gonna do my little backgammon and RL reading, and I'll just go eat, and then hopefully I can get started right after this. And this article was just too abstract. I don't know. Yes. Alright, thanks for watching. See you in the next one, I guess.